The next controller we're going to look at is how a PD controller gives us access to affecting our time domain specifications. So we can look at a controller with a transfer function that looks like this, where we have an adjustable gain and a location of a 0. Keep in mind that we can rewrite this as Ks plus Kz. And so this Kz would be what we usually call our proportional gain, and this K would be what we usually call our derivative gain. But effectively we have two knobs to turn, and if we go ahead and take a look again at this same second order transfer function that we did before and compute the denominator boils down to having this form. And what we notice is that K appears in the linear term, the term that multiplies S, and a product Kz appears in the term that corresponds to the constant term. So that means that K can give us direct access to affecting the zeta variable, the damping ratio variable, that we didn't have access to through proportional control. And this Kz term, which actually represents the proportional gain, that gets directly to affect our natural frequency omega. And so that kind of gives us hope at a high level that we can affect both the damping ratio and this natural frequency. But what we see is that picking K and Z, essentially the location of the 0 and the adjustable gain, that these are somehow entangled in achieving these goals. So we don't set them separately. We set one and then the other is set accordingly. So similar, again, then just the last point here is just that similar to proportional control, PD does not help with steady state error. If we had a steady state error before, we essentially have that same similar kind of finite steady state error that we'd observe in the PD. So we need the integral factor of PI control in order to help with steady state error.